Hi, Assalamualaikum and good morning, everyone. This is my lecture 6 of CHM 577. I am continuing on the lecture 5, where in lecture 5 I talked about how to draw the Lewis structure or the electron dot structure of any given molecule. Okay, continuing on to that one is the VSEPR theory, or the valence shell electron pair repulsion. Now, from the name itself, you're going to expect that the electron pair that you have at the valence shell will repel one another. And then through the repulsion of the electron pairs around a molecule, you are going to be able to predict what is the structure or the geometry of that particular molecule. Now, electron group repulsions occur. Yeah, repulsion. They don't like to be compressed too close to one another. They repel each other, these electron pairs, and that gives rise to 5 basic molecular shapes. You have linear shape, which looks like this, where you have a central metal in the middle there, and then one not central metal, central atom in the middle there, and then another atom at the end, and another atom at the end on the right, and you get a linear shape. Yeah, it looks linear. The second shape is trigonal planar, where the central atom is right there in the middle, and then there are 3 other atoms attached to the central atom, and the 3 bonds between that exist here will repel one another to produce a trigonal planar. In here, you have 2 bonds between the central atom and the atom on the left, and the central atom and the atom on the right. The 2 bonds will repel one another as furthest apart as they can. That is why you end up with linear. And then if you have 3 bonds repelling one another, you're going to end up having a trigonal planar, where the angle between one bond to another, this is the view from the top. Yeah, this is the view from the top. This is the view from the side, where the angle between the bond at the top and bond on the left is 120. And similarly, the angle between top to the right and right to the left, they're all 120. That is an ideal separation between 3 bonds that repel one another. If you have 4 bonds that repel one another, you're going to end up with a structure that is called tetrahedral. The 4 bonds, the one going to the top, one to the left, to the front, and to the front, and to the right back, they will also, the 4 bonds will also repel one another equally strongly. And in 3 dimension, this repulsion will result in a shape, a geometrical shape that is called tetrahedral, where all the bond angles are 109.5. So remember, a linear molecule will have a bond angle of 120. A trigonal planar will have a bond angle, 3 bond angles of 120. Or did I say 120 here? It's 180. Trigonal planar 120, tetrahedral 109.5, and the fourth basic molecular shape is what we call trigonal bipyramidal. Can you see that this shape is like 2 pyramids that are pointing one to the top and another one to the bottom, and the pyramid have a triangle base. Yeah, this is the corner of one, that's the corner of another at the front, at the back, and another one at the front. So the base is triangle. You have one atom that brings it to the top of the pyramid and another atom that brings it to the bottom of the other pyramid. So it's called Trigonal Bipyramidal. And the bond angles that are present in Trigonal Bipyramidal, there are two types. One is between the top going to the left and to the right. If you talk about like a globe, it's from the North Pole to the equator, and those are 90-degree angle. That means from that atom to this atom in the middle and to the atom to the left is 90 degrees. However, if you have trigonal bipyramidal, you also have a bond angle 120, because between that atom to that atom in the middle and that atom to the front is an equal division of 360 degrees into 3. So you divide that into 3, you get 120. So there are two bond angles in trigonal bipyramidal, 90 degrees from the top to the middle and to the bottom, and 120 all around the equator, if you like the globe. So the fourth shape is trigonal bipyramidal. Now the last, fifth shape is called octahedron. It's practically also two pyramids, but the pyramid in this case are square based. Unlike the trigonal bipyramidal, which is triangular based, the octahedral is square based. Yeah, there are 6 atoms surrounding a central atom. And in this case, in the case of octahedral, all the bond angles are 90 degrees, whichever way you look. So octahedral, now where does the octa usually is associated to the number 8. So where is 8 in this configuration, in this shape? Is actually 8 facets or 8 faces of this geometry. If you look at this side from the top to the left to the front, that is one face. And then you have another face on the right, another face facing the back, and another face facing the back of the left. So 4 faces or 4 surfaces at the top, 4 surfaces at the bottom. That is why it is called octahedral. 8 faces. It's not about 6. It's not about 6 atoms or 6 corners of this. It is about the faces. So you have 5 basic molecular shape: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now bear that in mind. Now, the valence shell electron pair repulsion VSEPR model predicts the geometry of the molecule from the electrostatic repulsion between the electron pairs, and the electron pairs meaning the bonding and the non-bonding electron pairs. Okay, if this is a table, this is the first column, second, third, fourth, and fifth. You have 5 columns. So the first type of molecule that we're going to talk about is AB3. A is being the central atom, AB2, not AB3, AB2. And B is the atoms on the left and on the right. Of course, when you have AB2, you have 2 atoms bonded to the central atom. There are no lone pairs in here. Can you see that around A there are no lone pair of electrons? So there are no lone pairs of electrons. And the arrangement of the 2 bonding pairs when they repel one another, as I said earlier, will be linear. So that is the shape of linear. So this is the case for a molecule of the class AB2. The second class or the second type of molecule, oh, no, this is an example, sorry. This is the example of that AB2 where you have a single atom here, right? where you have a single atom in the middle here, which is A, and your B in this case is represented as a black atom, X, AB2 or AX2. You have no lone pair of electrons. This is a symbol for lone pair of electrons. It's not present in this case. So you have a linear shaped molecule. The example is CS2 or HCN or BeF2. Yeah, so this is the first type. The second type is the type AB3, where there are 3 atoms bonded to the central atom, no lone pair of electrons. So you get a trigonal planar geometry with a bond angle of 120 degrees, and the molecular geometry is trigonal planar. When there are no lone pair of electrons, what you see as the arrangement of electron pairs will be the same as the molecular geometry. These two will only be different if you have some lone pair of electrons, okay? And the example of that is AB3E, AB2E, yeah? It's still practically AB3, but one of the B's become E. E stands for lone pair of electrons, yeah? AB2E, which is a variation of AB3, has 2 bonded atoms to the central atom, 1 lone pair of electrons. The arrangement of electron pairs is still trigonal planar, 1, 2, and 3, trigonal planar, but because the lone pair of electrons, this one here, does not carry an atom at the other end, you do not see it happening. It's just like you have a rope held by this person in the middle, but there's nobody else holding it at the other end. So that rope just falls. So practically, this lone pair of electrons is basically invisible. And the shape that is represented by AB2E, the molecular geometry, is bent because it's 1, 2, and the third one is invisible, so you only see the bent shape. Yeah, I hope that's clear. This is an example of the AB3 or AX3 with a clear trigonal planar, 1 central atom in the middle, 3 atoms holding bonded to the central, you get trigonal planar. But when one of them is replaced by a lone pair of electrons, you get a V-shaped or a bent molecule. So example of a bent molecule is SO2, ozone, PbCl2, tin bromide, whereas example of AX3 is SO3, sulfur trioxide, BF3, NO3 minus, CO3 2 minus. So those are examples. These are the examples for your trigonal planar shaped molecules, whereas these are not only molecules but also ions, and these are examples of your bent or V-shaped ions and molecule. Now, the third class of molecule is of the kind AB4. 1 central atom with 4 atoms, different atoms attached to it. There are 4 atoms bonded to the central atom with 0 lone pair of electrons. The arrangement of the electron pairs is tetrahedral, and the molecular geometry of that molecule is obviously tetrahedral. But if we progress to a situation where one of them is a lone pair of electrons, in the case of AB3E, where E stands for lone pair of electrons. There are 3 atoms bonded to the central atom, 1 lone pair of electron. The arrangement of electron pairs around the central atom is still tetrahedral. Yep, you can still see your lone pair there, but in real life or in the actual shape of the molecule, you do not see that at the top. You only see a trigonal pyramidal. Yeah, you have like a pyramid with a trigonal based situation. So you have trigonal pyramidal if you have a situation of A, B, 3, E. And the second situation that you might encounter is AB2E2, where you have 2 atoms bonded to the central atom and 2 lone pairs of electrons, and the shape of your arrangement of electron pair is still tetrahedral, but imagining that these lone pairs of electrons are invisible, all you see is a V shape or a bent shape. An example of that is water. Yeah, if you have 2 pairs of lone electrons on your central atom and 2 bonded pairs of atoms, then you get a V shape or a bent shape molecule. Yep. This is the example of AX4, a molecule without any lone pair of electrons. You get a perfect tetrahedral for the case of methane or SiCl4 or SO4 2- or perchlorate. But if one of these is replaced, one of the 4 is replaced by a lone pair of electrons, you get a trigonal pyramidal shape like this, the example of which is ammonia, PF3, ClO3, and hydrozonium ion. And if another of the bonding pair is replaced by a lone pair of electrons, making a situation of AX2E2, you get a V-shaped molecule, and the example of that, a common example of that is water, or OF3 or SCl2. Yeah. Next, this is an example of the 3 shape that we're talking about, your CH3, your methane, ammonia, and water. Now, what is the difference between these 3 shapes? You have in the first case where all the bonds are bonded atoms, yeah, bonded atoms, you get an ideal tetrahedral case where the bond angle is 109.5. However, when one of them is in like ammonia, when one of those 4 is replaced by a lone pair of electrons, you will, now the rule is lone pair is a fat is a fat situation where it takes more room in the environment, and it pushes the bonding pairs further away from itself. Yeah. So this lone pair of electrons have higher degree of repulsion compared to bonding pairs. So you can see that this bond of a perfect 109.5 has now become smaller in ammonia, which is 107.3. Why is it smaller? Because your lone pair of electrons push the other bonding pairs stronger than push bonding. And then the third case, as in the case of water, where you have 2 lone pair of electrons and 2 bonding pairs, you are going to have that situation even more clearly shown here, where the repulsion of the bonding pairs are so big, making your repulsion of your lone pairs are so big, making your bonding pairs squashed together, where the bond angles become smaller from 109.5 to become only 104.5. So it is clear that lone pair versus lone pair repulsion is bigger than lone pair versus bonding pair repulsion, which is bigger than bonding pair versus bonding pair repulsion. So the thing to remember here is that lone pair of electrons take up more space than bonding pair of electrons. That is why the angle between bonding pairs becomes smaller and smaller as you increase the number of lone pairs in the molecule. So the next type is AB5. AB5, you have the case of 5 bonded atoms to the central atom, no lone pair of electrons. So you get that perfect ideal trigonal bipyramidal that I was talking to you about earlier in this lecture, where you have the molecular geometry also looking exactly like the arrangement of the electron pair. Trigonal bipyramidal, where you have the bond angles of 90 degrees from the North Pole to the equator, whereas from equator to another point in equator will be 120 degrees. Yeah. In the case of AB5, the variation will be you have one lone pair of electrons. To make AB4E, 4 bonding pair of electrons, 1 lone pair of electrons. This is the arrangement of the electron pairs where the lone pair of electrons is situated on the equator or on the axial on the equatorial position. So you get what is called a distorted tetrahedron. If you turn this round like that, so you will see that the tetrahedron is slightly distorted. Yep. Next situation is when you have not only one lone pair, but you have 2 lone pairs. So it's AB3E. AB3E, 3 bonding pairs, 2 lone pairs. You get still the trigonal bipyramidal electron arrangement, but the shape that you get is a T shape because 2 of these lone pair of electrons are invisible. All that you can see is a T shape. So you can see that a T shape down that way. And the next case is when you have AB2E3, 2 bonding pairs and 3 lone pairs of electrons. So you have a linear because all of the lone pairs of electrons. Why do the lone pairs occupy the equatorial positions? Because the location around the equatorial are more spread apart, 120 rather than 90. If it takes up at the top here, it is going to be not ideal. So it is going to take the equatorial position. Since the 3 on the equatorial positions are invisible, all you get to see is the linear shape of the molecule, right? So the 4 molecular shape of trigonal bipyramidal electron group arrangement is when you have all of them bonding pairs, you get trigonal bipyramidal. When you have one of them, one of the bonding pairs is replaced by a lone pair, you get a seesaw. And then when you have 2 lone pairs, you get a T-shape. When you get 3 lone pairs, you get a linear. This is a seesaw, but in the previous slide, it is mentioned as distorted tetrahedral or a seesaw. Yeah? Or a seesaw. Seesaw. What is a seesaw? A seesaw adalah jongkang-jongkit. Seesaw. So let me make that a little bit bigger. Yeah, either distorted tetrahedral or a seesaw. So that is the summary for the 4 molecular shape of trigonal bipyramidal electron group arrangement. And the next case is, oops. Oh, those are examples, right? And the next case is AB6. Yeah, AB6. But before I go to AB6, I'll go back to the previous slide where you have these shapes shown to you. Yep, the shapes are shown to you like this. You have a perfect trigonal bipyramidal, you have the seesaw, you have the T-shaped, and you have the linear. Yeah, seesaw when there is one lone pair, T-shape when there are two lone pairs, and linear when there are three lone pairs. Okay? The next case is the case of AB6 when you have 6 atoms bonded to the central atom and no lone pair of electrons. The arrangement of electron pairs are octahedral, and because all of those are bonded pairs, you get to see the molecular geometry of that molecule is octahedral as well. But again, if you start getting lone pair coming in, AB5E, the case of AB5E, you still see that lone pair at the bottom, but since it is invisible, what you get to see is actually square pyramidal, because this one at the bottom here is invisible. So what do you see? You see a square pyramidal. Just imagine that that pyramid at the bottom is non-existent. So you get a square pyramidal. In the case of having two lone pairs of electrons, you're going to have the top and the bottom ones replaced by the lone pair of electrons, and what you get is a square planar. Yeah, no apex of the pyramid at the top, no apex of the pyramid at the bottom. All you get to see is the base of the pyramid, and it is square planar. So this is the three molecular shape of octahedral electron group arrangement, AX6, the example of which is SF6, sulfur hexafluoride. When you have when you have one of the 6 is replaced by a bonding, non-bonding or lone pair of electrons, you get this square pyramidal, where the example is BF5, bromo F5, or TeF5 minus, or a xenon OF4. And then the third case is when you have two lone pairs of electrons making a square planar shape molecule. The example of the examples are XeF4 or ICl4 minus. So that is the summary. Yeah, everything is summarized in here, right? Your linear, the case of number of electron pairs, 2 electron pairs, 3 electrons, 4 electron pairs, 5 electron pairs, and 6 electron pairs. You get all this shape. This is just a recap or a summary. And this is when you start getting number of lone pair of electrons as described one by one earlier in each of the slide. This is all the summary of it. Just go through it. And how are you going to use that information that I was telling you earlier on to predict the molecular geometry of a molecule? So for example, if you are given SO2, what is the shape of SO2? First of all, you draw the Lewis structure of the molecule. You have learned it before. SO2 will look like this. So how do you classify this SO2 shape? It is now all the double bond or single bond or triple bond is counted as one bond between the central to another atom. It doesn't matter whether it's a double bond or triple bond, but to determine the shape of the molecule, you have to count double and triple as a one bond. So in this case, you have 2 bonding pairs and 1 lone pair. So it's AB2E. So you get the shape of, what is AB2E? AB2E, you get a bent shape. Yeah. What is the shape of SF4? when you draw the Lewis structure of the molecule, you're going to have this kind of situation arising. You have sulfur with 4 bonding pairs and 1 lone pair, and that makes it classified as AB4E. So AB4E is going to be distorted tetrahedron or a seesaw. So first you draw the Lewis structure, you count the number of lone pairs on the central atom and the number of atoms bonded to the central atom. Remember, number of atoms bonded to the central atom, not the number of bonded pair. Number of atoms bonded to the central atom, and you use VSEPR to predict the geometry of the molecule. So your SO2 will have a bent shape because it will assume a situation of AB2E, and your AB4E for SF4 will give you a distorted tetrahedron or a seesaw. So we have a situation here where you are requested to draw the molecular shape and predict the bond angles relative to the ideal bond angle of PF3 and COCl3. So for the solution, for PF3, there are 26 valence electrons. When you go through the rules of drawing Lewis structure, you are going to find this situation here. You're going to find that the phosphorus in the middle has 1 non-bonding pairs, 1 non-bonding pair or 1 lone pair of electrons. So it's actually AB3E or AX3E. So going to your VSEPR, this situation is actually a derivative of a tetrahedron, but that one at the top is missing or invisible. So you have a situation where you get a trigonal pyramidal shape, but this bond angle is a lot less than 109.5 because the lone pair is going to push the bonding pairs further away from itself. Yeah. So AX3E or AB3E situation gives you a trigonal pyramidal. And next you have CH3CO. You're going to have methyl, C double bond O. And if you go through the Lewis structure, you're going to find this situation. Carbon is bonded double bond to oxygen. If you cannot work this one out, we can discuss it in the classroom or when you meet me in live session, and then we can discuss it with you. So you're going to have your carbon here, HHH, and then 1 bond there is going to be a tetrahedral for this particular carbon, tetrahedral for that particular carbon, but in this particular carbon is not going to be tetrahedral, and there are no lone pair of electrons. So this is going to be a case of AB3. So this carbon in the middle is AB3. This carbon on the right is AB4. This carbon on the left is also AB4. So you're going to have this shape where the central carbon right in the middle here is a square planar. No, trigonal planar with this one here. Yep. Remember, your oxygen here will have lone pairs of electrons. It's going to somehow push the others slightly away from itself because these lone pairs, as I was telling you, are occupying a larger space. Then you're going to have this bond angle to be less than 120, that bond angle to be less than 120. So practically the shape of an acetone is like this. Yeah, the shape is that carbon, oxygen, CH3 on the left, CH3 on the right, and you have this bond angle in the middle here to be less than 120. Right? The tetrahedral centers of ethane and ethanol. Now, if you have an ethane, yeah, This is a highly symmetrical situation. Each one of your carbon will be tetrahedral center. That will be a tetrahedral center. And you are going to have this bond angle to be 109.5, ideal tetrahedral. Yep, one tetrahedral on the left, one tetrahedral on the right. But when you start getting something like ethanol, you also get tetrahedral centers for carbon on the left and on the right. However, the tetrahedral center on the right, for carbon that is attached to OH, will be not ideal situation. You're going to have your HCH bond angle to be less than 109.5 because this is going to take a lot more space than just a simple hydrogen. So that is the situation. You are going to have tetrahedral center here, tetrahedral center there, one bond, 2 bonds, 3 and 4 bonds on this carbon. But this oxygen here is going to be bent. Why do I say bent? Because you do not get to see the lone pair of electrons attached to this oxygen. All you see is that carbon, oxygen, and hydrogen bond. So it looks like a bent situation. So oxygen is bent. This carbon in the middle is tetrahedral, distorted a little bit. This carbon on the left is slightly more ideal tetrahedral situation. So I hope you understand how to apply the Lewis structure and use VSEPR to predict the geometry and the shape of the molecule that given to you. So if you have any question, please post them to me in the Telegram group or during our live meeting session every Thursday at 10 o'clock. So that's it for now. I'm going to finish off this particular slide here after 36 or 37 minutes of lecture. There's 1 hour lecture before this during the Lewis structure. So this is 1 hour and 40 minute slide. So I hope things are fine and you can catch what I'm saying. But do discuss, do some practice exercises in the textbooks that you have, or I'm going to give some questions to you in the group. Thank you. I'll see you in my lecture 7. Bye-bye. Assalamualaikum.